distribuições que têm, a priori, só... Oh, sorry. I'm speaking both languages. Can I start again? We're going to start by talking about distributions that have a priori only the mean. For some probably historical reasons, it has not been very much considered, maybe because of the central limit theory, maybe because of Fisher's success in putting the standard deviation as a measure of risk. And we're going to see that actually the standard deviation is not a good measure of risk. And the omega function that we define has many properties. It's a new way of representing the distributions. We have different ways, characteristic function, this and that. But the omega also characterizes the distribution. And properties that could have been found 150 years ago, again, found now. And that comes from an Irishman that had this thinking about batching books. I think in his case it was probably, I think it was dogs. And distribution, the idea of probability started from the beginning very much in people that were playing cards and stuff like that. And that's still the case, that all this creates some intuition about things that are interesting. So we turn it upside down. We create a function instead of a number. And it leads to exceptional distributions. What I mean by that is that we applied the equivalence problem that Bill was talking about in the first class. And we found new distributions about, he's going to talk more about that later. So this is just the integral from a to x of f, and the integral from divided by integral. So this is just, in terms of finance, you can see that as losses over wins. So the smaller it is, the better it is. The only textbook we found that talk about those functions was published in the project Euclides in IMPA by Barry James, a probabilist that spent some time here. It's a very geometric book. We like it a lot. And this relationship that's in the book, it's actually, and it helps us to make the calculations we're going to show you simpler. Because when we define the function, we start proving theorems in a very difficult way till we get to this very simple equation that shows that I1 and I2 balance at the mean. We have this picture here. So I1 is the green, I2 is the blue, and they balance at the mean. We're giving most of the proofs for the properties and everything for you guys to do at home, because once we manage to organize the way we present it to you, they're all very simple. Integration by parts, derivations. There's not one complicated calculation. I would feel very ashamed of being doing this here. It would be really crazy. Okay. So these are the first properties. Those ones we had in the beginning, and you can prove easily, okay? They balance at the mean, so the mean at the mean, the omega at the mean is u. It's monotone increasing. Actually, the omega functions, it looks a bit like an exponential function. It has that kind of shape. again, from the beautiful formula, you can find the berry gems.
Remember, he only gives it for me for x equals 0.
Oh, sorry. Yes.
We had to
We had to do a little bit more. Yeah.
we had to do some more work to get the rest, but it's not that far.
It proves that not only when f equals g, you have the same omega functions, but the inverse is also right. You just use the fact that is one at the mean, you derivate, and you find the proof for that pretty easily. The inverse formula was a little bit more complicated. Also, there was an English mathematician that gave a proof that was quite hard to make. And finally, when we understood a little better, we gave to my brother-in-law. He did it, his brother. So
yeah, the first proof, Nick Bingham gave a proof, but it relied on solving an ordinary differential equation. And it was much more complicated when we didn't know the magic relation.
formula.
You had to work straight from the original definition, but we thought it ought to be something you could solve by differentiating and eliminating, and Brad managed to do
Shadwick,
that.
Yeah, he's a physicist currently in Nebraska University. He's responsible for all the complicated calculations we need to do. And
on a computer.
implementation, all this stuff. So another exercise, verify the inverse formula. We're not asking you to derive, just verify. And use to determine which distribution this omega function is. And then take the Bernoulli distribution, O minus 1, 1. Okay, now this is the part that we're getting warm because we have a new definition we call the standard dispersion. And it really came out from, it's the derivative, right? And the interesting thing is that's half the mean absolute, basically the mean absolute deviation. So there was, in the past, there was a big fight between Fisher and Eddington. Fisher is the statistician that sort of win the fight that the standard deviation was going to be the measure of dispersion around the mean that everybody uses. Eddington, it was not a mathematician. He was making calculation, astronomical calculation. He was in Brazil for this, I think it was in Ceará, this observation about Einstein's theory that the light curves with gravitation. And he made a lot of calculation, and he defined the mean absolute deviation. And he proposed that was better than the standard deviation. He lost the war probably because he was too young. And that also might be the reason why nobody looks at distribution only have mean defined. But this ohm, we call it ohm, of course, because omega, it's very useful.
But we also didn't know that it was the mean absolute deviation for a
When
long
we
time.
define, yeah.
So we discovered a lot of properties of it the hard way.
So the ohm is when you have a delta function, the ohm is 0. It really measures the concentration around the mean. Here you have two student T distributions are very useful in applications. They have fat tails. They're very useful in financial applications, etc. You have two omega student T distribution with 2 degrees of freedom. 2 degrees of freedom and 5 degrees of freedom. And the green is the one with the small concentration around the mean. And you can see the omega functions for them. And the omega is the derivative. So then we have the question, what are the Markov and Chebyshev inequalities? And can we do the same thing when you don't have a sigma? In fact, we can. And the Markov inequality in the case the A is bigger than me is completely useless, right? Because this quantity is
Less.
Huh?
You said bigger. You mean when A is less than mu?
Yeah.
So it's just telling you the probability is less than 2, for example,
Yeah.
which isn't much news.
Doesn't make any difference. But here you have something more subtle. And the same thing for the Chebyshev. Not only you have something more subtle, but you also have a difference between the left of the mean and the right of the mean. You have the inequality that doesn't work only with squares, and you can actually make more precise. This is all exercise, of course. And then you have the diagram that should help you. The properties. When you use an affine transformation, which is our pet transformations, you have that it transforms the omega function of the subsequent distribution the way you would like it. If 2 distributions have the same mean, you have that in average, the integral is 0. But if they have the same ohm, again, you have the same kind of result on the left and the right. When you go into applications, especially in finance and other things, you don't want the left and the right distribution to be the same. You actually want to have gains more than you have losses. So you really want to be able to control this thing very well. And if they have the same standard deviation, you just have an average like that. Also, you can look in examples. It's something we haven't proved yet as a conjecture. But the standard deviation gives much more weight to outliers than the Ohm does. If you take the S&P index, this is 40 years, and you take one outlier out. See, the standard deviation reacts much more stronger than the Ohm. It's another very good property. And now, it's easy to prove that Ohm is also an affine invariant, the same way the standard deviation is. So we define what we call the Cascon-Shadwick character. And this is really a character. You look at data, the uniform distribution has its characters 4 over square root of 3. The normal distribution is square root of 2 pi, and the Laplace 2 over square root of 2. So all the time we see examples, people that work with data, and they say, now we're going to assume we have a normal distribution, and we're going to do this and this with the data. Months ago, we had people working in medicine ask us a question, and they say, we assume a normal distribution. Well, if your data, if you calculate the CS character, which is easy to calculate, and the CS character is not close to square root of 2 pi, it's not normal. There's no way. So this is just an example. We took a lot of data, we used data generators, and we took draws of 250, 500, and 1,500 points. And you see how close to the normal population value, square root of 2 pi, which is 2.51 approximately, how close those things are, and how different they are from the Laplace distribution. So it's really a character. It gives you a lot of information. So that's what I just said. The characters, it's not the same. It's not a united. So in finance, again, everybody assumes normal. Different. I mean, a number of times we talk to people about the fact that standard deviation is not a good measure of data, and then they turn around and say, we define the risk as standard deviation, blah, blah, blah. It's not. It's definitely not. Okay, in the following slides, we show the affine Laplace distribution by a normal, my match omega, and improves the fit. So that's another kind of problem. So when you approach something, assuming that you have a normal, how good the fit can be. So you have something that's really Laplace, and you assume there's a normal, you try to approach it. That's what you get. With the same standard deviation, you get the red. When you do the same ohm, you get the blue, which is better. It's more, the Laplace is the green. And the normal with the same ohm is the blue, and the norm with the same standard deviation is the red. This is just a graph of the errors of the same thing, but graphing the errors. So here the conjecture that I said, we haven't proved that, but this would prove that the ohm is a much better fit. You can have fun. So more properties. So we have an addition property. So it's nice, it works fine, everything's fine. So and when you have F, it's a superposition of other distributions. And you have this. So now we want to create useful statistics. What is going to be a shape score? Well, what we're going to do in the next slides is take data from that a priori don't have the same support. And we're going to put them in the same support so we can compare them. And we're going to create a way of scoring those, tell if something is better than the other one. People use, they want fat tails, and they use skewness, blah, 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 which is very often complicated calculation, and they don't have enough data. When you have problems like the virus problem that we tackle with our tools, and then you have problems in finance, you have a small amount of data, and you want to see what the tails are, how fat the tails, because that's where the information is. Near the mean, you just have the noise, and the information is on the tails, and you want to be able to deal with very small data sets. So, well, you can see it, probably a lot of you can just see by looking what happens when lambda is equal to 1. It's something that a lot of people have seen already. we put as an exercise. This is, so it's very easy to, again, it's very easy, now that we know how to, it's very easy to calculate the ohm from this distribution, from the omega function. Then the first theorem and the corollary, it's how you use the affine transformation to put the distributions in the same domain. So that's, again, it's pretty simple calculation. Now we're going to define a shape. So that's, you can define lots of different shapes. And you can define your own, you can go into business and try to sell it as a tool. And you're smart enough, it should work. And we're just defining this one as integral of the log of the omega function, which is zero for symmetric distribution, positive when mu is negative, and vice versa. So the distribution is biased on the downside when mu larger than 0, and biased on the upside when mu is smaller than 0. Now, that's the good property. It's an affine. This shape so defined is an affine invariant, so you're going to be able to transform all your distributions in a base and apply this shape score. Example 2, probability densities transform to be on 0, 1, and you have the shape scores. Exercise, prove the theorems, of course. And then the 13 is very interesting. If you find the distribution whose omega function is exponential, and show the variance is 2/3 of p squared. This is a probabilistic definition of pi. Because usually you see the normal, the fine as a function of pi, etc. If pi didn't exist, but you do this, you have a definition of pi. It's very nice. And for the normal distribution, you prove that omega is sigma over 2 squared. And we put that reference, Barry James' book, but we're going to put some more reference. Did I go too fast? Any questions? I did. If you don't have any questions, sorry. I told you that I tend to speak too fast. I didn't want to make to be giving the proofs because they all, the problems were very complicated to start with. The uniqueness, I mean, if I have 2 omega functions, prove that they are from 2 similar distributions. It took us a while to prove it. I managed by using just geometry and building auxiliary functions, which I was very happy with. Because all the time I was teaching, I was telling the students that auxiliary functions was a magical wands. And finally, we managed to do it in a very simple way, but those ideas were complicated to start with. So, but I didn't want to make the calculations.
So, but is it similar to something like the inversion formula for the Fourier transform?
Sorry?
Because you have the same result for the Fourier transform, right? Is it the proof you were telling? Is it similar to that kind of calculation?
No, it's simpler.
Simpler?
Yeah. Those proofs here that we put in exercise is basically integration by parts and derivation.
So the only things that are awkward is when you've got an integration by parts, but the domain is infinite at one end or the other.
Yeah, because they
And then you
there,
need-
they didn't need to be finite.
That's right. So that it adds, but the only complication that adds is dealing with the limit, limit term at each end. It's real, and that's Barry James, for example, has that worked out well. So that's actually very simple. But until that magic formula, the difference between I2 and I1 as a function of x was proved, everything was hard to do. That makes everything easy.
Yeah.
But it's worth doing. I mean, that's the other thing. So make them exercises so you actually do them, because then you have a feeling of how these things
Work.
fit together.
But if I do it here in the blackboard, you're not going to have a feeling while you do it. You're going to fall asleep. It's just, yeah, because it's simple manipulation.
I mean, there's another, for example, if you just differentiate I1 and I2, you can see that the derivative of the difference is 1. So or I2 minus I1, its derivative of that is minus 1. So you can immediately integrate, except that you don't know what the constant of integration is. Well, it's mu, but
mu.
you have to figure that out somehow, and it's the same, basically the same. It all comes down to the same problem.
But I thought the most important, besides telling you that those properties exist, etc., and there is an easy way now that the past is all signal and everything. The most important things for me is the fact that we define this invariant the ohm, and we define the characters, and that you have a way of scoring all those things. Because that's another problem in finance. People say, or even in other areas, this thing is better than that because you have a whole domain with blah, 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 blah. Usually, you really want to have a number to do a scoring, because that will give you an absolute certainty that something is better than the other. So this is a tool that allows you to do that. And I think this is the important part here. Yes. Yes. Why I call you shape?
If you go back to
Yes.
the picture, it's easier.
This one?
Yeah, the picture. I mean, it's really the degree of asymmetry that it's picking up. Right? So in this example comes from finance, where the returns on an index like the S&P 500 are not too far from being symmetric. Right? The shape score is 0.9. It's not symmetric. But the thing that's really asymmetric is the VIX, which is an index of volatility. And it has enormous jumps upwards. It never jumps a lot downwards, but it jumps enormously over a period of 2 or 3 days. It can change by a dramatic amount, enough to wipe out people who are betting on it not changing, and so on. And this allows you to make a comparison directly from the data of those two things. Whereas a term like skewness, you'll get vastly different numbers for skewness if you look at the sample over 2 different periods. So a lot of econometricians would tell you that financial data doesn't actually have 3 finite moments. It's something more than 2, but less than 3 typically. So this is very dodgy to try to use higher moments to make calculations in many types of real-world data.
Which you don't always manage to calculate anyway because of the small data set. It's not something
Well,
that's
they're not the
stable.
calculations. You can always compute it, but it's not very stable.
Yeah.
Add or subtract a point, and things can change a lot. And And that's, I mean, but you know, it's very, very common. It's almost standard for people to refer to some result, some observation as being a certain number of standard deviations above the mean. Well, if you knew the data was normal, or if you knew it came from another distribution, fixed distribution, then that would mean something. But the fact that they just say it means that there's only one thing you can be talking about if you simply assume that a standard deviation means something, and that's a normal distribution. It's actually quite difficult to find real data that looks convincingly normal in many, many subjects.
Yeah.
I mean, there are...
When for example, on the virus, when the COVID started, all the discussions were what about the mean, the evolution of the mean, and the number of standard deviations where the thing could happen, could be bad or something like that. And in finance, it's the same thing. And it's meaningless.
So you have similar. I mean, the ohm is not this mean absolute deviation, not a universal yardstick either, but it has features that make it better, that make it more comparable when you're using it. Even if it is apples to oranges, your measure of the two fruits is more comparable than simply what you get if you use standard deviation.
And the character is very important because it definitely characterizes what kind of distribution you have.
It allows you to rule things out. I mean, it's certainly the case that it's not unique. You can have other distributions. You can manufacture distributions that have this root 2 pi as a character. So it's most useful where people somehow need it most, which is in ruling out the hypothesis that the data comes from a normal distribution, and that already would remove all sorts of
complications,
of errors that are routinely made, because and most of the people making them don't actually even realize they're making an assumption. I remember giving a talk at an investment management conference pointing out this difficulty with using the ohm or the standard deviation as a common risk measure. And someone afterwards came up to ask a question. He was absolutely baffled because he had been taught in his MBA program the definition of a standard deviation was a move that's, either side of the mean gives you 68% of the probability. He'd literally been told, as if there was no other distribution in the world that you might want the standard deviation from.
That's the other problem with the applications of probability. People use things without knowing what the assumptions are. All the time we find this.
Well,
they use central limit theory for 500 data points. I have no idea what's going on. So we've been knocking people on the head about that.
There are a couple of papers we published,
we should
two or three. We should put references.
Yeah.
One reason I didn't already was that they predate the turning the omega function upside down, so that things are, you've got these orientation reversing things. But I mean, it doesn't really change much, and they were published in finance journals. They go through a lot of the properties and give many examples with real data to show how different things look when you actually ask the question: is this normal? Is the assumption reasonable? I think it also, one of them includes a proof of the fact. It's actually, you can, on the back of an envelope, you can literally prove that returns in financial data should be log normally distributed. The thing is, it depends on assumptions that, of course, because you're going to invoke the central limit theorem. And there's no way to check those assumptions. You'd have to, and of course, limit theorems, they tell you that something will happen as n goes to infinity, but don't tell you how big n has to, you typically have no idea how big n has to be. And there's very often very little known about the error for n less than the limiting value. So yeah, anyway, for us, the geometric aspects of these things we'll come back to next time. One, the fact that geometry extracts from this picture some
information,
exceptional distributions, some limit theorems and so on, exactly the same way it does with the other things we've talked about so far.
Yeah, the other thing is that we did the omega functions. We create some scoring systems, and we create some ways of concluding things. We'd never realized at that point that we were dealing with stream value theory. Then we applied the Cartan's method, we found the invariants, and we started understanding there was actually some stream value theory implied in this. So Bill's going to talk more about that. So we went to Holland to learn about stream value theory because we knew nothing about it, completely ignorant. But it was a nice journey, as they say. Right? I think that's all, Anderson. Thanks.